technical limitations exist in the maximum number of tiers allowed in cable trenches for several reasons. Firstly, heat dissipation is a major concern. Cables generate heat as they carry current. Multiple tiers of cables can trap heat, leading to overheating and potential cable failure. Secondly, cable bending radius must be considered. Cables have a minimum bending radius that must be maintained to avoid damage. Multiple tiers restrict the bending radius of cables in lower tiers. Thirdly, cable accessibility and maintenance become increasingly difficult in upper tiers. Cable repairs or replacements may require the removal of multiple tiers. Fourthly, the mechanical strength of concrete trenches is limited, and excessive tiers can weaken the structure and increase the risk of collapse. Generally, the maximum number of tiers allowed is limited to 2 to 3 tiers for both low voltage and medium voltage cables. This limitation ensures proper heat dissipation, cable bending radius, accessibility, and mechanical strength. It is generally not advisable to have low voltage and medium voltage cables in the same trench due to safety and interference concerns. Safety is paramount. High voltage, medium voltage cables can pose a significant safety hazard to personnel working in the trench. In case of a fault or insulation failure, the high voltage can arc and cause injuries or fatalities. Electromagnetic interference, ME, is another concern. Medium voltage cables generate electromagnetic fields that can interfere with low voltage cables. This can result in signal distortion, false readings, or equipment malfunction. Heat dissipation is also a factor. Medium voltage cables generate more heat than low voltage cables, which can affect heat dissipation in the trench and potentially damage low voltage cables. If it is avoidable to have low voltage and medium voltage cables in the same trench, the following precautions should be taken. Firstly, maintain a sufficient separation between low voltage and medium voltage cables to minimize EMI and heat transfer. Secondly, use shielded low voltage cables to reduce EMI. Thirdly, install cable barriers to prevent accidental contact between low voltage and medium voltage cables. Fourthly, provide adequate ventilation to dissipate heat from medium voltage cables. The best arrangement of cables in such a scenario would be to place low voltage cables in the lower tiers and medium voltage cables in the upper tiers, with a separation barrier in between. This arrangement helps reduce EMI heat transfer and the risk of accidental contact. Consider the ampacity of the conductors. The ampacity of a conductor is the maximum current, in amps, it can carry continuously under specific conditions of use without exceeding its temperature rating. The National Electrical Code (NEC) provides tables, such as NEC Table 310.15b16, that list the allowable ampacities of insulated conductors rated up to 2000 volts, based on the conductor material, insulation type, and installation conditions. These tables typically assume an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit and no more than 3 current-carrying conductors in a raceway or cable. If the ambient temperature is higher than 30 degrees Celsius, or if there are more than 3 current-carrying conductors in a raceway or cable, the ampacity of the conductors must be derated according to NEC Tables 310.15b2 and 310.15 cone. Derating factors are multipliers that are applied to the allowable ampacity to account for the reduced heat dissipation capability of the conductors under these conditions. For example, if the ambient temperature is 40 degrees Celsius and the conductor insulation is rated for 75 degrees Celsius, the derating factor from NEC Table 310.15b2 is 0.88. This means that the allowable ampacity of the conductor must be multiplied by 0.88 to determine its adjusted ampacity. Similarly, if there are 6 current-carrying conductors in a raceway or cable, the derating factor from NEC Table 310.15 cone is 0.80. This means that the allowable ampacity of the conductor must be multiplied by 0.80 to determine its adjusted ampacity. It is important to note that the derating factors in NEC Tables 310.15b2 and 310.15 cone are cumulative. This means that if both the ambient temperature is higher than 30 degrees Celsius and there are more than 3 current-carrying conductors in a raceway or cable, the ampacity of the conductors must be derated by both factors. For example, if the ambient temperature is 40 degrees Celsius, the conductor insulation is rated for 75 degrees Celsius, and there are 6 current-carrying conductors in a raceway or cable. The adjusted ampacity of the conductor is calculated as follows: allowable ampacity x 0.88 x 0.80 adjusted ampacity. In addition to derating conductors for ambient temperature and the number of current-carrying conductors, it may also be necessary to derate conductors for other factors, such as the presence of harmonics or the type of load being served. Harmonics are non-sinusoidal currents and voltages that can increase the heating of conductors and equipment. If harmonics are present, the ampacity of the conductors must be derated according to NEC section 220.61. The type of load being served can also affect the ampacity of the conductors. For example, motors and other inductive loads can draw high inrush currents when they are started. These inrush currents can cause the conductors to overheat if they are not properly sized. As a result, the NEC requires that conductors serving motors and other inductive loads be sized at 125% of the motor's full load current rating. When installing cables in underground trenches, it is important to consider the ampacity of the conductors and to derate them as necessary to ensure that they are not overloaded. The overloaded conductors can overheat and cause insulation damage, which can lead to short circuits, ground faults, and fires. In addition to considering the ampacity of the conductors, it is also important to consider the voltage drop in the cables. Voltage drop is the decrease in voltage that occurs along the length of a cable due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop in feeder circuits not exceed 3% and that the voltage drop in branch circuits not exceed 5%. To minimize voltage drop, it is important to use conductors that are large enough for the load being served and to keep the length of the cables as short as possible. Another factor to consider when installing cables in underground trenches is the type of insulation used on the conductors. The insulation must be suitable for the underground environment and must be able to withstand the moisture, chemicals, and abrasion that may be present. The NEC requires that underground conductors be insulated with a type of insulation that is listed for direct burial. Some common types of insulation that are used for underground conductors include THHN, THWN, and XHHW. In addition to the type of insulation, it is also important to consider the size of the conductors. The conductors must be large enough to carry the load being served and to minimize voltage drop. The NEC provides tables that list the minimum conductor sizes for various types of loads. When installing cables in underground trenches, it is also important to consider the spacing between the cables. The NEC requires that cables be spaced a certain distance apart to allow for adequate heat dissipation. The spacing requirements vary depending on the type of cable and the ampacity of the conductors. It is also important to consider the depth at which the cables are buried. The NEC requires that cables be buried at a certain depth to protect them from damage. The depth requirements vary depending on the type of cable and the voltage of the circuit. Finally, it is important to consider the type of backfill used in the trench. The backfill should be free of rocks and other debris that could damage the cables. The NEC recommends that the backfill be compacted to prevent settling. In summary, when installing cables in underground trenches, it is important to consider the ampacity of the conductors, the voltage drop in the cables, the type of insulation used in the conductors, the size of the conductors, the spacing between the cables, the depth at which the cables are buried, and the type of backfill used in the trench. By following these guidelines, it is possible to ensure that the cables are installed safely and reliably. It is crucial to select appropriate cable types. Different cable types are designed for specific applications and environments. For underground trenches, direct burial rated cables are essential. These cables are specifically designed to withstand the harsh conditions of direct contact with soil, moisture, and potential chemicals. Common types include underground feeder, AF cable, and cables with XHHW or THWN insulation. UF cable is a non-metallic sheath cable often used for residential applications, while XHHW and THWN are individual conductors that can be installed in conduit. The cable's voltage rating must also be suitable for the intended application. Low voltage cables typically have voltage ratings of 600 volts or less, while medium voltage cables can range from 2400 volts to 35,000 volts. Selecting the correct voltage rating is critical for safety and performance. Cable size, or conductor gauge, is another critical factor. Cable size is typically expressed in American wire gauge, (AWG), or in circular mills for larger conductors. The appropriate cable size depends on the ampacity requirements of the circuit and the desired voltage drop. The NEC provides tables that specify the allowable ampacities for different conductor sizes and insulation types. Voltage drop is the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop in feeder circuits not exceed 3% and that voltage drop in branch circuits not exceed 5%. To minimize voltage drop, it is important to select conductors that are large enough for the load and to keep the cable runs as short as possible. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, allowing overcurrent protection devices to operate and clear the fault. Bonding ensures that all metallic parts of the electrical system are at the same potential, reducing the risk of electric shock. In underground trenches, grounding electrodes such as ground rods or ground plates should be installed to provide a low impedance ground path. All metallic conduits, cable trays, and enclosures should be bonded together and connected to the grounding electrode system. Proper installation techniques are critical for ensuring the long-term reliability of underground cable systems. Cables should be installed in accordance with the manufacturer's instructions and all applicable codes and standards. The trench should be excavated to the proper depth and width, and the bottom of the trench should be free of rocks and debris. A layer of sand or other suitable bedding material should be placed in the bottom of the trench to protect the cables from damage. Cables should be carefully laid in the trench, avoiding sharp bends or kinks. The cables should be spaced properly to allow for adequate heat dissipation. After the cables have been installed, the trench should be backfilled with suitable material, such as sand or compacted soil. The backfill should be free of rocks and debris that could damage the cables. The trench should be properly compacted to prevent settling. Cable identification and labeling are essential for maintenance and troubleshooting. All cables should be clearly identified with labels that indicate their voltage, circuit number, and destination. The labels should be durable and weather resistant. Cable markers should be installed along the length of the trench to indicate the location of the cables. Regular inspections and maintenance are essential for ensuring the long-term reliability of underground cable systems. The trenches should be inspected periodically for signs of damage or deterioration. The cables should be inspected for signs of wear, corrosion, or insulation damage. Any damaged cable should be repaired or replaced immediately. The grounding and bonding system should be inspected to ensure that it is in good condition. The trenches should be kept free of debris and vegetation. Also consider cable support and securing. Cables in trenches should be properly supported and secured to prevent damage and ensure that they remain in their intended positions. Cable supports can be made of various materials, such as plastic, metal, or concrete. The type of support used will depend on the size and weight of the cables, as well as the environmental conditions in the trench. Cables should be supported at regular intervals to prevent sagging or stress. The spacing between supports will depend on the type of cable and the support system used. Cables should be secured to the supports using cable ties, clamps, or other suitable fasteners. The fasteners should be made of corrosion-resistant materials to prevent deterioration over time. When installing cables in multiple tiers, it is important to ensure that the supports are strong enough to support the weight of all the cables. The support should also be designed to allow for adequate ventilation to prevent overheating. Cable separation is also something to think about. Maintaining adequate separation between cables is essential for preventing overheating and reducing the risk of electrical interference. The NEC specifies minimum spacing requirements for cables based on their voltage and ampacity. These spacing requirements should be followed to ensure safe and reliable operation. When installing low voltage and medium voltage cables in the same trench, it is especially important to maintain adequate separation between the cables. A physical barrier, such as a concrete wall or a metal partition, can be used to separate the cables. Alternatively, the cables can be installed in separate conduits or cable trays. Cable protection is vital. Protecting cables from physical damage is essential for ensuring their long-term reliability. Cables and trenches can be damaged by a variety of factors such as rocks, debris, rodents, and excavation equipment. To protect cables from physical damage, they should be installed in conduit or cable trays. Conduit provides a rigid enclosure that protects the cables from impact and abrasion. Cable trays provide a more flexible support system that allows for easy access to the cables. Cables can also be protected by burying them at a sufficient depth. The NEC specifies minimum burial depths for cables based on their voltage and location. In areas where excavation is likely, cables should be buried deeper or protected with concrete slabs or other physical barriers. The selection and installation of these components must adhere to relevant standards. Firstly, the National Electrical Code (NEC) is a widely adopted standard for electrical installations in the United States. It provides comprehensive requirements for cable selection, installation, and protection. Secondly, the Insulated Cable Engineers Association (ICAER) develops standards for cable construction and performance. ICAER standards are often referenced in the NEC. Thirdly, the National Electrical Manufacturers Association (NEMA) publishes standards for electrical enclosures, conduits, and other related products. NEMA standards ensure that these products are suitable for their intended application. Fourthly, local building codes and regulations may also impose additional requirements for underground cable installations. It is important to consult with local authorities to ensure compliance with all applicable codes.